You know, in life, in business, in pretty much everything we do, we're constantly on a search for the best, right? The fastest way to get somewhere, the cheapest way to build something, the most effective strategy. It's all about optimization. But how do you go from just a gut feeling of what's better to knowing what is the absolute mathematically proven best? Okay, let's dive into this. So let's bring this down to earth with a problem we can all get our heads around: driving. We all kind of know that if you drive crazy fast, you're just burning gas. But crawling along can be inefficient too. So, somewhere in between, there has to be a perfect speed, a real sweet spot that gives you the absolute best gas mileage. I'm not talking about a good guess, but the one single best speed. I mean, how would you even find that? You could try driving at 50, then 51, maybe 51.1 miles per hour, but you'd be at it forever. Thankfully, we have this incredibly powerful tool that's built for exactly this kind of problem. It's one of the crown jewels of calculus, and it gives us a guaranteed way to find the answer. To find the best, first we've got to learn the lingo that mathematicians use. When they're talking about optimization, they talk about finding extrema. It sounds fancy, but it's really just their word for the maximums and the minimums of something.
The easiest way to think about it is like looking at a landscape. If we were to graph our car's gas mileage against its speed, the best mileage would literally be the highest peak on that entire graph. And the worst? Well, that'd be the lowest valley. So our job is to become expert map readers and find that single highest point.
And just to be super clear, what we're hunting for is the absolute maximum value. This isn't just some local hill that's higher than the stuff around it. No, this is the single highest value the function can possibly reach, period. It's the Mount Everest of our graph. To see what this looks like, let's check out a couple of simple graphs before we get to something more complex. Sometimes finding the maximum is actually really easy. Take the function y equals cos x, just on this specific interval here. You can literally just see by looking at it that the highest point it ever hits is right at the top, at a value of 1. That's it. That's its absolute maximum.
But here's where it gets interesting. The playing field totally matters. See on the left? That's the function y equals x squared. It just goes up and up forever, so it doesn't have an absolute maximum. But look what happens on the right when we say we only care about the interval between 0 and 2. All of a sudden, bam, an absolute maximum appears, right at x equals 2. The rules of the game, the domain, can completely change the answer.
So how in the world do we find these peaks and valleys without having to check every single one of the infinite points along a curve? This is where calculus hands us this amazing shortcut. It tells us exactly where we need to look.
The first clue is something called a critical point. Think of these as special locations on our graph where something interesting is happening. It's either a flat, horizontal spot where the curve levels out for a second, kind of like the top of a smooth hill, or it's a sharp, pointy corner.
And here it is, the big idea. The absolute best answer we're looking for, that highest peak or lowest valley, is guaranteed to be hiding in one of just a few places, either at one of those special critical points or at the very edges of our graph, the endpoints. That's it. Suddenly, our search has gone from infinity to just a handful of candidates.
Okay, that's a brilliant question though. We found the potential hiding spots, right? But are they all winners? Does every single flat spot on the curve automatically mean it's a maximum or a minimum?
And the answer is a firm no. Take a look at the graph of y equals x cubed. Right at the center, you can see it flattens out completely. The slope there is 0, so yeah, it's a critical point. But it's obviously not a peak or a valley. It's more like a little pause before the graph keeps on climbing. So a critical point is a candidate, not a confirmation. It's a clue, not the treasure itself. So here is the simple, incredibly powerful 4-step recipe that calculus gives us. First, you find all the critical points. Second, you list your endpoints. Third, you take that nice short list of points and plug them back into your function to see what values you get. And fourth, you just compare them. The biggest number you get is your absolute maximum, and the smallest is your absolute minimum. It works every single time.
But how can we be so sure about that? I mean, how can calculus make such a bold guarantee? Well, it all comes down to this really beautiful and deep idea called the mean value theorem.
Let's go back to our car for a second. Imagine you drive for an hour, and at the end, you figure out your average speed for the whole trip was 30 miles per hour. The mean value theorem guarantees that at some single moment during that trip, your speedometer needle had to be pointing exactly at 30. It's impossible for you to have stayed below 30 the whole time, and it's impossible you stayed above it the whole time. It had to happen.
And that's really the core idea here. It's like a bridge that connects the overall average behavior of something, like your average speed over an hour, with its instantaneous behavior at one specific moment. It promises that at some point the instantaneous rate of change has to perfectly match the average rate of change.
And when you see it on a graph, it's just so elegant. If you draw a straight line connecting the start and end points of a smooth curve, this theorem guarantees there's at least one spot on that curve where the slope is perfectly parallel to that connecting line. The instantaneous slope matches the average slope. Now, this isn't just a cool party trick, it is the logical bedrock that guarantees our whole optimization method works. In fact, this theorem is a cornerstone of calculus. It's used to prove a ton of its other big ideas.
All right, so let's put this all together. We started with a simple question about gas mileage. We explored the language of peaks and valleys, and we uncovered the deep guarantee that makes it all work. Now let's see just how powerful this one idea is out in the real world.
This is not just for textbook problems. This exact same method is used to find the most effective dose of a new medicine or the cheapest, most efficient way to build a pipeline. It's used to figure out the shape of a box that can hold the most volume with the least material. And of course, the perfect speed for your car. It is a universal tool for finding the best. So here's the main takeaway. We now have a systematic way to find the best of something. From identifying those critical points to testing the final candidates, you have the roadmap. Which kind of makes you wonder, now that you know the method, what in your world would you want to optimize?